Hello, welcome to another problem session. Um, we have a problem that requires calculus. So this is a problem of motion around along. If this was origin, then it's along the radial direction. So this block or this bead rides on a rod frictionlessly. So as you spin it, the bead will just kind of migrate outward like that. Nothing is preventing a bead from actually flying out eventually. So at some time it's this, set some t equal to 0, it was there, and this is time at some of the time. So that's and the bead, the whole rod is spinning with frequency, angular frequency omega, or angular speed here, omega. Okay, let's see. So view from the top. Let's draw. So this is the plane in which bead is. So that's the origin, and so this is the xy plane, and so this will be going in a circle, but it will really not be going in a circle, right? It will go in a what you might say is increasing radius. Next time it comes, it's over here. So actually at this instant, momentarily you can see that there will be a acceleration in that direction, and there will be an acceleration in that direction. And the acceleration, the radial acceleration, so if I were to there's and there's a tangential acceleration too, which we are not going to look at because we're only interested in the radial motion. And this is along, if you consider this to be r hat vector, the unit vector radially out, and you consider this as a theta hat vector in the polar coordinate of r and theta, then this, we're only interested in acceleration in the direction of this unit vector, and for that we can just radial direction. This is the radial component. So component of acceleration towards r hat direction. And this r hat direction is very tricky because when this object is over here, the r hat direction is that way. So r hat direction later is in that way, and some other places, when it's over here, the r hat direction is exactly opposite of this r hat direction. So you have to be very careful. And this, when you work it out, this is equal to this is the positive side. So this is like how the r coordinate is varying, the radial coordinate varying. So d square r dt square, and this one is just our same old friend, v square over r at this instant, which is omega square r, but r is a function of time and omega here is constant, so it's minus omega square, and this r is same as that r. So these are functions of time. R is a function of time. Now in this there is no friction along the rod. There's no friction along the rod. That means that in the radially, if I look at force along this direction, along r hat, is actually 0, which means if I write F equals ma, and I just look in towards r hat direction, towards the opposite or opposite. Either way we look at this. This will be 0. This will be written as FR equals MAR, and this will be 0. So this is equal to 0, and so this will be just M and AR, and M is not 0. That means A sub R is 0, and that gives me an equation here, which should be able to, if I solve that, I should be able to get this location of the bead, right? So this equation is d square r dt square equals to omega square r, and this is second order differential equation. So a general solution is r of t is a e to the power omega t plus some b e to the power minus omega t. Now a and b has to be obtained from initial conditions. So this is a general solution. So at t equal to 0, we have r0, we're writing as some point r0. So it will fix one of these, right? It will give me, that will give me r0 equals to a plus b. So I need one more condition. Another condition will come from initially bead is at rest, so I need to get a dr dt to get a speed. so radially speed along the directions, it's only moving along the rod, so this will be the only speed. It's going to be omega a e to the power omega t minus omega b e to the minus omega t. So this is number 2. So this is, let's call it number 3. So this is VR. VR at 0 time is 0. So this omega a minus omega b is 0. So this is 0 equals omega can sit on the side. It makes a minus b equals 0. So you can solve for a and b. So you can say they're equal to each other, and from there you just says a equals to b equals r0 over 2, and we'll put in here. So answer for part A will simply be r at arbitrary instant t while on the road, not on the rod, not outside the rod. At some point it's going to move off the rod, is equal to r0 over 2 e to the power omega t plus e to the power minus omega t, which you can write down as r0 cosine hyperbolic omega t if you want to more compactly. So that's the answer for A. The speed part, we just have to do it over here. So for B, V of t will simply be omega times r0 over 2, omega times r0 over 2 e to the power omega t minus e to the power minus omega t, and you probably know this is going to be omega sinh omega t, which is all, take a derivative of that, you already get this. So that's how simple this whole thing is. But a lot of the work goes into actually finding the expression, this expression for a component, radial component of acceleration in a polar coordinate. You can get more detail on how to do this in chapter 6 of these websites. Physics bootcamp.org. I maintain that website, and if you have any questions, you can send me a comment or leave your comment below this video. I'll see you in another video. Bye.